Hi students, this is Viswanath, Chemistry faculty for NEET and IIT exams. Now see the Bohr's explanation for line spectrum of hydrogen. First point, in hydrogen atom, the stationary states for electron are numbered 1, 2, 3. Symbol is small n equal to 1, 2, 3, so on. These integral numbers are known as principal quantum numbers. In hydrogen atom, for orbits, Niels Bohr gave designation. Those orbits are represented by 1, 2, 3. That means orbits are represented by n. N values are 1, 2, 3. These numbers are called principal quantum numbers. Next, the radii of the stationary states are expressed as Rn equal to n square into a naught. This one here. A naught equal to 52.9 picometers. Already radius expression we completed in the previous classes. Thus, the radius of the first stationary state called Bohr radius is 52.9 picometers because first orbit means n value equal to 1. So, R1 equal to 52.9 picometers. That is the first stationary state. This is also called Bohr radius because Bohr identified this one. That's why it is called Bohr radius. Next, the energy of the stationary state is given by En equal to minus RH into 1 by n1 square. Here n values 1, 2, 3, so on. RH is called Rydberg constant and its value in joules 2.18 into 10 power minus 18 joules. The energy of the lowest state, also called as the ground state, is E1 equal to minus 2.18 into 10 power minus 18 into 1 by 1 square. Ground state means n value equal to 1. Substitute that, we can get this one. So, energy of the ground state is in hydrogen atom is minus 2.18 into 10 power minus 18 joules. Next, when the electron is free from the influence of the nucleus, the energy is taken as 0. That means for this electron in this situation, the principal quantum number n equal to infinity. Here principal quantum number represents orbit number. Electron is not under the influence of the nucleus means its orbit is infinity. Electron is present at infinite distance from the nucleus and is called as ionized hydrogen atom. Electron is not present in hydrogen atom means that is a ionized species. Already we know that hydrogen atomic number 1, it has only one electron. That electron is at a infinite distance from the nucleus means that is ionized atom, H plus ion. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. When the electron is under the influence of the nucleus means it is present in n orbit, a particular orbit that electron is present, then some amount of energy is emitted. Emitted means released and its energy is lowered. As the electron gets closer to the nucleus, En energy becomes larger in absolute value and more negative. That's why negative sign is used in the energy expression of stationary state. In the previous classes, we completed energy expression En equal to minus 13.6 into Z square by N square electron volt per atom. There minus sign indicates electron is present in the close vicinity of the nucleus. That means in the first orbit electron is present, it has released some energy. That releasing nature is expressed by using negative sign. When electron is present at infinite distance, the energy of the electron is 0. From infinite distance electron is bringing close to the nucleus, then its energy is increased. Again, its energy becomes negative when it is very close to the nucleus. That's why we are using negative sign in the energy expression of the stationary state. Important point, remember carefully. Next, This Bohr's theory can also be applied to the ions containing only one electron like hydrogen atom. See the examples: He plus, Li2 plus, Be3 plus. In all these ions, one electron is present just like hydrogen atom. So we can apply Bohr's theory. Next, En equal to minus 2.18 into 10 power minus 18 Z square by N square joules. So here suppose He plus, if we want to apply energy expression, then Z value becomes 2. Based upon the energy level, we can get N value. Next, when an electron jumps from one orbit to another orbit, then the energy gap between the two orbits is given by delta E equal to EF minus EI. Here EF means energy of the final state, EI means energy of the initial state. See this one from expression 1. 1 means this one. From this formula, we can get expressions for EF and EI. So energy gap delta E equal to minus RH into 1 by NF square minus RH into 1 by Ni square. From this we can get this one, delta E equal to RH into 1 by Ni square minus 1 by NF square. Here Ni is initial orbit, NF final orbit. So from this RH value, if we substitute, then we can get this one, delta E equal to 2.18 into 10 power minus 18 joules into 1 by Ni square minus 1 by NF square. Next, the frequency related to absorption and emission spectrum of photon is calculated by, say this expression, delta E equal to H nu equal to delta E by H. So nu, frequency of the spectral line in emission spectrum or absorption spectrum, nu equal to delta E by H. Delta E means in the previous step we got this expression, substitute that, then we can get this one. Next, wave number formula expression, wave number is nu bar equal to nu by C. Nu means this one. Substitute here C means velocity of light, H Planck's constant, or H Rydberg equation. Finally we can get expression for nu bar, this one. Next, remember these conditions: NF greater than Ni, final orbit number is greater than initial orbit, then absorption spectrum we can observe. Okay, that means then energy is absorbed. Okay, if initial orbit number greater than NF, then emission spectrum takes place. For example, Ni value 6, NF value 2. Sixth orbit to second orbit electron transition takes place, then energy is released. That means emission spectrum is observed. Here fifth orbit, this is first orbit. First orbit to fifth orbit electron transition takes place, then energy absorption takes place. So we can get absorption spectrum. Okay, next, the brightness or intensity of spectral lines depends upon the number of photons of same wavelength or frequency absorbed or emitted. Spectral lines brightness or spectral line intensity depends upon number of photons having same wavelength. If more number of photons having same wavelength, then more intensity we can observe for the spectral line. In terms of frequency, same thing. More number of photons having same frequency, then also we can observe more intensity of spectral line. Okay, that means wavelength, frequency both are inversely related. So number of photons of having same wavelength or more intensity of spectral line we can observe. In terms of frequency, also we can express same thing. Next, see the multiple choice questions. What is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n equal to 4 to n equal to 2? From fourth orbit to second orbit transition takes place, then what is the wavelength of the emitted light. See this, for this first we have to calculate delta E, energy gap. Here Ni is 4, Nf is 2. Then spectral line is observed in Bohr series. Delta E formula is this one, 2.18 into 10 power minus 18 joules into 1 by Ni square minus Nf square. Here Ni means 4, Nf means 2. Okay. So substitute the values, we can get this one. Nu, frequency nu equal to delta E divided by H. So this value substitute here, Planck's constant, we can get frequency. Finally wavelength we should calculate, lambda equal to C by nu. So substitute values, we can get that one. So this is Bohr's atomic model. Next topic is de Broglie's waves theory. De Broglie's wave theory. The wave nature of the electron was first proposed by de Broglie. According to him, all moving particles have wave particles. Till then, scientists thought that moving particles have only particle nature, but this scientist proposed wave character is also exhibited by all moving particles. These wave particles are significant only for microscopic objects. In case of microscopic objects only, these wave properties are significant, that means important. Microscopic objects means electron, proton, neutron, atom, molecules like this. If we want to consider wave properties for microscopic objects like moving football, moving car, those are not that much important. Moreover, we cannot observe their wave character properly. That's why these wave properties are important for microscopic objects. To calculate wavelength of the waves associated with these microscopic objects, he proposed an equation, that is de Broglie wavelength equation, lambda equal to h by mv, that equal to h by p. Here lambda equal to wavelength, h Planck's constant, v velocity of the particle, mv, that equal to p momentum of the particle. According to him, electron revolve around the nucleus with stationary waves. Electron revolve in those orbits whose circumference must be equal to integral multiple of wavelength. See the formula for that. 2 pi r circumference is equal to n lambda, r equal to radius of the orbit, n equal to 1, 2, 3. That means 2 pi r equal to lambda, 2 pi r equal to 2 lambda, 3 lambda, 4 lambda, like this, integral multiple of wavelength. Next, number of waves in an orbit equal to n, number of revolutions of electron per second in an orbit equal to velocity of electron divided by circumference. Next, remember this formula, based on this numericals are there. A relationship between kinetic energy and wavelength of moving particle, lambda equal to h by square root of 2 into kinetic energy into mass of the moving particle. Next, let a charged particle like electron be accelerated with a potential of V, then kinetic energy equal to E into potential. Therefore, lambda equal to h by square root of 2 into E into V m. For an electron, lambda equal to 12.27 divided by square root of potential angstrom units. See the multiple choice questions. Which of the following has the largest de Broglie wavelength provided all have equal velocity? CO2, NH3, O2, N2. Here lambda equal to h by mv, that is the formula. In that, largest de Broglie wavelength, that means which one having large lambda value, h constant, velocity is equal, only variable is mass. So wavelength, mass, both are inversely related. Which option having less mass, it has largest wavelength. NH3 having less molecular mass, it has largest de Broglie wavelength. This is the answer. Next, if the wavelength of the electron is numerically equal to the distance traveled by it in 1 second, then understand carefully, wavelength of the electron numerically equal to the distance traveled by it in 1 second, that is nothing but velocity. So velocity is equal to wavelength, that means wavelength is equal to velocity. Then de Broglie equation lambda equal to h by mv. In place of velocity we can take lambda, then we can get this one lambda equal to square root of h by m. Okay, so what is the option? Option B is the answer. Next, the kinetic energy of an electron accelerated from rest through a potential difference of 5 volts will be. Here we completed kinetic energy and potential difference formula. Kinetic energy equal to electron into potential difference. Apply the same formula. Kinetic energy half mv square equal to potential E into potential difference. Given potential difference 5 volts. Substitute here 5 electron volts. What is the option? C. Next, the de Broglie wavelength relates to applied voltage is this one. Already we completed this. Lambda equal to 12.3 divided by square root of applied voltage into angstrom units. Option B is the answer. Practice well. We will meet in the next class.